So last time I started section 4.3, and we started with the greatest common divisor, and I showed you quite a few different methods for finding greatest common divisor. Sometimes in your book it'll tell you specifically what method it wants you to use. Oftentimes it won't. It'll just give you your choice on doing so you get to pick. On your test, I definitely could go either direction as well, so I would make sure that you know what the differentiations are for each of them and then be willing to do whichever one you're needed to do for that particular problem. Today we're going to extend this to the last part, which is to find least common multiples. And several of the least common multiples kind of feel a lot like the other ones, and you'll notice them when they happen. So to start with, a least common multiple is the least non-zero whole number that is a multiple of all whole numbers in your set. One of the things that trips people up a lot of times is that the word least and the word greatest feel like least should mean small and greatest should mean big. And in some sense they do, but they're adjectives that clarify the noun, right? It's the least multiple. Multiples are numbers that are in your multiplication list. They're bigger than the numbers you started with. Okay, a greatest divisor, it's a divisor. It has to be something that divides what you're working with. So least common multiples are bigger than greatest common divisors in spite of the words how they're used matters. So the first one that we're going to take a look at is called the number line or the colored rods method. And I have colored rods and I forgot to bring them. It's the first time I've actually been able to use them. We just purchased them recently. So I'll draw the pictures for them so you can see how they work. We hadn't had them before now. This method is a very visual method. What it does is it shows the multiples of numbers on a number line or in sequential rods for each of the values, and then you find the first value at which the intervals coincide. We'll do my best to remember my colored rods next time just to show you what they look like because they're pretty cool. So the way that this would work, here's an example. This is the least common multiple of 6 and 15 that we're going to use. So using colored rods or the number line method. So we're going to draw a number line. Just extend it as far as you wish for the moment. And we're going to start with 0. And actually let me draw it with the number lines first and then I'll show it with the colored rods so you can see the difference. They're quite similar. But multiples of 6. So if I have multiples of 6, this would be the first one. I would move out 6 and I would sort of like skip count or jump by 6s. So 6 plus 6 would be 12, and then I'd add another 6 to it and I'd get 18, and I'd add another 6 to it and I'd get 24, and I'd add another 6 to it and I'd get 30, and I add another 6 to it and I could get 36, and we could do this process forever, right? So in a very real sense, we're skip counting, we're jumping jumps of 6. Okay? And we do the same thing, excuse me, with the number 15. I'll do it in a different color, so I'll do my 15 in blue. So my jumps, instead of being jumps of 6, will be jumps of 15s, which means I land between 12 and 18 at 15 if I jump 15. And if I jump 15 more, where will I land? 30. And the first time that I land at the number that matches, right, from both lists, basically for both jumps, that's my least common multiple. So that's the number line perspective. In the colored rods perspective, what actually ends up happening is that I have rods, and the rods have different lengths, and they don't have infinitely many rods, so they aren't every single length possible. But you would have a rod, say, of length 6, like this, and you would stack them end to end like this. So there's 6 and a 6. This is not going to probably match up perfectly with my picture above because my spacings are a little bit off, but bear with me and pretend for, a little bit. And then I would add another 6. And I just keep adding these colored rods that are 6 long, my reds. Again, indefinitely is the idea. Eventually it has to end because you're going to run out of rods. We'll put one more on there just for fun. Okay, so we have all these rods that are of length 6. And then I need a rod of length 15. So I would choose out of my box of rods. If I had a rod of 15, that's what I'd be using. And I'll change the color. I'll use the same blue or a blue that I could use instead. And so my rod of length 15 would be about like that. I'm eyeballing it a little bit, but that would be about 15. And I would stack them end to end as well. And what I'm wanting is I'm wanting the end to ends to line up at the same spot. And the spot where they line up at the same spot, if I'd done it well, it looks like it's ending right here, right? Would be my least common multiple. So this is 15 plus 15, which would be at 30. Or you can jump across your 6s 5 times to end up at 30. This is the colored rod method. So colored rod method's really nice because it's tactile learning, right? We can actually do it. If I brought them with me, at least we could, with actual manipulatives, with pieces of I think they're either wood or plastic, I don't remember. So it's the colored rods method.
Do you want us to use like different colors?
You don't have to. It might be easier though to do so. So I'd suggest you do. Most of you probably have some other color, whether it's a pen or a pencil, something differentiable in your wallet or purse or something, or find a crayon or a colored pencil marker. So yeah, it would be helpful to you and to me. This has limitations. That's what I was going to say. This has limitations. Obviously, if I'm using the colored rods specifically that are back in my office, I don't have a rod of every length, right? I mean, like that's not a practical thing to talk about. So it has some limitations on where you can actually utilize the tactile learning part of it. But with most manipulatives, that's how it is. You're forming the basic understanding of something with small pieces, and then eventually you move beyond the need of the manipulatives to being able to do it abstractly. So this would have limitations to being able to be used for a while, but not indefinitely. This next one is actually a really good abstraction of the previous method. So this is the intersection of sets. Now we had an intersection of sets method with the greatest common divisor. This one works a little differently. This one actually works more like our pirate problem that you guys brought up from the last homework set. What you do is you list all the multiples of each value, and then you find the least value the lists have in common. So very much like this problem, instead of drawing the picture for what we're doing, we would just list the numbers that were on the number line. So it would actually say 0, 6, 50, well, it wouldn't say 0. It would say 6, 12, 18, 24, 30, 36, ... And then it would say 15, 30, 45, 60, ... And we'd look for the lowest number they have in common. So we're going to do this with the numbers 12 and 15. So our number 12, we're going to list multiples of 12. Now, it's the same as skip counting by 12s or adding 12 every time. It's a arithmetic sequence, if you want to prefer that notation or that idea. It's the multiplication tables of 12s from that perspective. They're all the same thing. So I have 12 and then 24, 36. What would be next? 48. 60. Let's get a couple more. 72, 84. Okay. And obviously we can do this list out as far as we need to. So if we find out after we've written a number of them down, we're going to write our second list and they don't actually coincide yet, we would just extend our lists. So my list for 15 now. 15, 30. What's next? And if you happen to notice, hey, I've got a matching number, you can stop your list. If you didn't and you wrote out a few more, it would not be the end of your world, right? And again, if you'd written out this many and they didn't have that 60 in there, so they didn't match yet, you just keep extending your lists until they do. Eventually, they have to. They will eventually match. So the 60 would be my least common multiple. So again, as with everything, this one has pros and cons. One of the limitations or the cons to this is that, again, if the numbers occur pretty quickly to find your least common multiple, it's not too bad. But if this least common multiple had not happened until we got to 12 times 15 and we had to write down a ton of numbers, you probably wouldn't be the happiest camper, right? It'd feel like it was really annoying, like it took you forever to list them all out kind of thing. So there is that sort of caveat. All right, the next method is very similar to one we saw with greatest common divisor. We saw a prime factorization method with that, and we're seeing it here as well. Much of the pieces of this process are the same. The first step in the process is the same. Construct the prime factorization of each number. The step 2 is actually the same as well. Choose all prime factors, except that it says all prime factors, right? Not just all of them that they have in common. So we got to get all of them in our list, whether they're in common or whether they're different. All of them get included. 3, listing them with certain exponents. That's one of our steps from greatest common divisor, but specifically with greatest common divisor, we were looking for the smallest exponent that they shared, right? Here we're going to use the largest one that they share. And then step 4 matches the same. It's to find the product. Multiply it out. Okay, so we're going to use the numbers. Ooh, let's see, 90, 50, and 20. And we're going to use prime factorization method. So we're going to break down 90, 50, and 20. All right, so smallest factor, prime factor that 90 divides by. 2 to give me 45, and then it divides by 3 to give me 15, 3, and 5. So this is 2 times 3 squared times 5. How about 50? 2 to give me 25, 5, and 5. So on this one I have 2 times 5 squared. 20 is a 2 again. To give me 10, 2, and 5. So this is 2 squared times 5. Okay. 3 separate prime factorizations. Is that part okay? Okay, so I need to list all of the prime bases in any piece of any problem. So what are my prime bases? 2, 3, and 5. And then I want to find the 2 that has the biggest exponent. So 2, right? So I'm going to include a 2. I need to find the 3 that has the biggest exponent, and that is a 2. And I need to find the 5 that has the biggest exponent, and that is a 2. Now we're going to multiply it out. So this is 4 times 9, I know, I see it just a second, times 25. Okay, and so we need to multiply 4 times 9 times 25. Hopefully you've already done that. What did you get? 900. Yeah, so my LCM, my least common multiple, is 900. Now, I mentioned in the last, or the first part of the section last time, that you can at least verify that it really is a multiple pretty easily. I should be able to take that 900 and evenly divide it by 90, evenly divide it by 50, and evenly divide it by 20. If I can't, then I've already made an error and I need to go back and double check stuff, okay? That doesn't ensure that it's the least common multiple, but at least you make sure that you found a multiple that way, which is half of the part of the question. So, okay, any questions with the prime factorization method? Okay, so just like last time, my favorite is the division by primes method. So the division by primes method has us write the numbers in a row, divide all the numbers by a common prime factor, divide all the quotients by another common prime factor, and you keep going. There is a caveat to this. Number 4 says repeat the step until you can't find any common factors. The caveat to this that makes it a little bit different is that it says any factor that divides at least 2 of the numbers. So if you have 3 numbers or 4 numbers, you don't have to have all of the numbers have something in common. Anything that any 2 of them have in common is we will divide by. And that's a little different. That doesn't work with greatest common divisor, but it is necessary for least common multiple. The least common multiple is the product of the primes. Now we saw that happen before as well, but when we did the product of the primes with greatest common divisor, what ended up happening is that we multiplied just the 2 on the outside, the 2 and the 5. When we do it for least common multiple, we're going to multiply it along the bottom as well. So if we were doing this particular problem, we would multiply the 2, the 5, the 41, and the 36. And that's going to give me my least common multiple instead. Okay? So that's what we're going to be doing, and we have another list of numbers. We have 90, 100, and 20. So I'm going to write them in a row, and there's nothing special about using 3 numbers. you could be using 2 numbers and it's just fine. I just wanted to show you how this works with 3 numbers because of that weird, if it divides any of the 2 of them business, that's something that's a little unique here. So first, smallest prime that divides all these numbers, 2. So I kind of do want to check for the smallest thing that divides everything first. So I've got 45, 50, and 10. Smallest that divides all the numbers. 5. So 5 will give me 9, 10, and 2. So I do not have a number that divides 9, 10, and 2, right? I don't. But do I have a number that divides at least 2 of those numbers? 2. 2 will divide 10 and 2. So I'm going to draw it as though I'm going to divide the 9 by it. I'm just not. The 9 just gets brought straight down. But the pieces that do divide by 2 actually get divided. So this would be 5 now, and this would be 1. Now, looking at 9, 5, and 1, I don't have the ability to take a pair of numbers and take out a common factor any longer, right? So the product of the primes is the product outside and around the bottom for my least common multiple. So my least common multiple is 2 times 5 times 2 times 9 times 5 times 1 if you want to write it. It doesn't keep them all in order quite as nicely as previous work that we've done, but we can handle it. So if we were to multiply this one out, I know it's not the same numbers we had last time, but the LCM would still be you need to get it? It's 900 again. That's just happenstance that I picked numbers that worked. Yep, Hallie.
So how come on the greatest common divisor we stopped and on this one we kept?
Yeah, so what we're really trying to do with least common multiple is we're trying to remove things that they have in common that would make them unnecessarily big. So let me just give you an example of something quite small. So every now and then when my kids are doing addition of fractions right now, they're in 7th grade, and they have a fraction with a denominator 2 and they have a fraction with a denominator 4, they'll just multiply the 2 and the 4 together. Well, 2 times 4, which is 8, is a common multiple. I mean, like it works, but it's more than they needed. And the reason it's more than they needed is because they had double counted the 2 in the 4. I already have a 2 embedded inside of the 4. I don't need another 2 multiplied by my 4 to make that work. So as we're pulling these pieces out where they have just maybe 2 of them in common instead of all 3, that's what we're trying to do. We're actually trying to remove the double counting of things that are multiplied by all of them. So we start with all the pieces, in part because it gets our number smaller quicker, not because it has to be done that way, but it's just quicker. And then we're trying to remove all the pieces even if only 2 of them have it in common instead of all 3. The reason we multiply by the pieces on the bottom is because least common multiple means it needs to have all the factors in it in order to be a multiple, whereas greatest common divisor only needs things that are in common to both of them instead of all of them to be the greatest or least. All right, there's an interesting formula that relates the greatest common divisor and least common multiple together. It says the following: for any 2 non-zero whole numbers a and b, if you find the greatest common divisor of the numbers, and you multiply it by the least common multiple of the numbers, you will get the same thing as if you'd multiplied the numbers together to begin with. So this is just telling you that you're considering the same numbers every time. So you do the GCD of the 2 numbers, you do the LCM of the 2 numbers, and then you multiply the 2 numbers. And they bear this relationship if you do them. So we're going to take a look at one where we already found the GCD in order to show how we can use this formula. But you can use this formula with any of them. So for example, if I wanted to find, it has to only be 2 numbers. And this one was a good one, 12 and 15. If I wanted to find the greatest common divisor of 12 and 15 after I found the least common multiple, I can actually take the greatest common divisor, which I don't know, times the least common multiple, which I do know, it's 60. And I can multiply those together. That looks almost like a 68 on that screen, the way it made it larger. And then I would multiply the 12 and the 15 together. So whatever 12 and 15 is multiplied, I would then divide it by 60, and I would have my greatest common divisor. So as long as I know the 2 numbers, and I know one of the other 2 pieces of information, I can use it to find the third. So over here, there we go. We have the number 72 and 126. This is the one we did last time with Euclidean algorithm. It's a little bit of a weird one where we did the division a bunch of times. And we found over here when we did that method that the greatest common divisor was 18. Okay? So we had the 72, we had the 126, and we found that the GCD was 18. So we're going to use that over here. So I know that the GCD is 18, and this is from problem number 4. So what this formula says is that I can take the greatest common divisor times the least common multiple, and it will equal the two numbers that I'm working with. For me this time, that's 72 and 126. So the greatest common divisor, 18, times the least common multiple will equal 72 times 126. And it has to be a whole number. I mean, like that's my only option. This won't work otherwise. You've got an error if you get something fractional or decimal. So 72 times 126 is 9,072. And I will divide by my 18. To get 504. So my least common multiple here of these two numbers is 504. Okay. So I'd like to show you some application problems with greatest common divisor and least common multiple. I will say that there are times on this test where I ask questions like, create a least common multiple question, create a greatest common divisor question. I've been known to do that before. It really trips people up, even when I show them these examples when they have to do it on their own. One of the things that has to be the case is it can't say inside of the question, find the greatest common divisor, because you lose every bit of real world quality if you tell somebody how to do a problem. Do you guys realize that, right? Say, if I say to somebody, say, find your average test score, and then you have to actually tell them every single step about how to find the average test score, you might as well have done it yourself. Yeah? Okay, so this is the same idea here. So we've got two bike riders, and they're going around a circular path. Okay, so try to picture what's happening in your mind. There's a circular path. Come on. And the bike riders are going around, right? One in blue, one in black. They're not going on the outside of each other. They're just, I can't draw them on top of each other very well, okay? They're not going the same speed, though. The first rider can go all the way around the circle in 12 minutes. The second rider can go all the way around the circle in 15 minutes. Okay, so they're running laps. Y'all have all run laps at some point in gym class before, right? Something, okay? They're running laps. They're starting and stopping at the same place. They're going in the same direction. If they weren't going in the same direction, this wouldn't make sense. If they weren't starting and stopping in the same place, it wouldn't make any sense. Okay, so those are conditions to make the problem make sense. So you got to think about how these things sort of would realistically work if you were having a lapse process. They go at a consistent pace. Consistent pace is important, right? So if they slow down or they speed up, that is, it takes them 12 minutes the first time, and then 13 minutes the second time, and then 15 minutes the third time, then this doesn't work. So the consistent pace is really important for this to make sense. They've got to go 12 minutes to get lap 1 done, another 12 minutes to get lap 2 done, another 12 minutes to get lap 3 done. It's a consistent pace. The question says, after how many minutes will they meet again at the starting place? Okay, so they're going around and around and around this circle, and eventually they have to meet back up at the starting place if all those conditions are met at the beginning. So this is the question I have for you. Is this a greatest common divisor question, or is this a least common multiple question? It is a least common multiple. They are going around the track multiple times. Does that make sense? So this question is legit asking me what is the least common multiple of 12 and 15. And we've done this in many ways now, right? In fact, we've done the 12 and the 15 before, so I'll do it in a different way. The way we did 12 and 15 the first time is that we did it with lists. Lists are great, you can use them, but you've already seen that, so we'll do something different. I'll do my division by primes. So if you do the 12 and the 15 with division by primes, what do they both divide by? 3, leaving me with 4 and 5. Do 4 and 5 have anything in common? No. So I can't divide any further. And if I multiply all around the outside, my least common multiple will be 3 times 4 times 5, which is the number 60. This is a context question. 60 what? Minutes. After an hour, right, 60 minutes, they will end up at the starting spot at the same time. Okay, does that make sense?
Do we need to list, like, you know how earlier we did LCM equals? Would we need to do that on these kind of problems?
Your work will definitely show that you've done an LCM, so I don't think that that's a really big deal on it. I'll know what you've done by how you've done the problem. So, but if you want to just keep it in your mind clear, that's certainly fine. Okay, so just a real quick show of hands. How many of you guys have seen Father of the Bride? Okay. Do you remember the part in The Father of the Bride where he goes nuts at the grocery store with the hot dogs and the hot dog buns? Yes. Okay. That is a very good example of a least common multiple problem. The hot dogs and the hot dog buns in his scenario did not have the same number in each package, and he got frustrated, right? He didn't want to buy extra buns, I think it was, if I'm remembering it right. He's like, why is this one sold in 8s and this one sold in 10s? They should be sold in the same package. He rips in the package and he takes out the buns. I think that's what I remember happening. It's been a little while. Okay, so that's a very good example of least common multiple. If you were to go to the store and do this, it actually happened with me this last week, a couple weeks ago. We were having a cookout, and it happened with the hamburger patties and the hamburger buns. The hamburger patties were sold in 12s. Hamburger buns were sold in 8s. And I wanted to have the same number of buns as I had patties. That was what I was shooting for here. So I had to figure out how many groups of these things could I do that with to make that work. I was looking for a least common multiple. Okay? So that's a very good example that's got like product, not time involved as well in a least common multiple scenario. All right, so by default, you probably know that this is going to be a GCD problem. But let's take a look at why. So Dr. Hands makes cupcakes for her students. She makes 20 chocolate cupcakes and 24 vanilla. She wants to display them on plates with the same number of cupcakes on each plate, but only one type of cupcake on each plate. What is the greatest number of cupcakes she can put on each plate? So there's some conditions again inside of this one that have to be met for this to make sense. One of the conditions is that there's chocolate and there's vanilla and they're not mixed together. If you mix it together, you have 44 cupcakes and you've lost every bit of the fact that you're trying to find something that divides 20 and 24 evenly. Okay? You mix them together, you got 44, and you can do all sorts of things that may or may not be appropriate. Okay, so no mixing of the cupcakes for this to make sense. So we're working with this one, 20 and 24. It's wanting to put them on plates. The same number have to be on each plate, so we're dividing them up. That's a key for being a divisor problem, right? We're dividing something into pieces or to groups in this case. So we're going to be working with a greatest common divisor. So we have a GCD of 20 and 24. So let's use prime factorization because I haven't done that one a second time today. So we'll do 20 and 24 with prime factorization. If you don't want to do it this way, you do your own way. So cool. No problem. So 20 divides by 2, giving me 10 divides by 2, giving me 5. So I have 2 squared times 5. 24 divides by 2, giving me 12. Divides by 2, giving me 6. Divides by 2, giving me 3. This is 2 cubed times 3. A GCD problem, because that part could be done for GCD or LCM. A GCD problem takes the prime bases they have in common. So what bases do they have in common? Yeah, just the 2 actually, right, as a base. And then the smallest exponent is a 2. So the greatest common divisor is actually 4. So she can place them 4 per plate. Now, does that make sense? If I have 20 cupcakes, can I place them 4 per plate evenly? Yep. If I have 24 cupcakes, can I place them 4 per plate evenly? Yes. Another example that I've seen, this is a really good classroom example. The first time I saw it may have been about a year ago, and I thought, oh, What a lovely example, is putting students on rows. So a teacher wants to put her students in rows or in groups in a classroom, right? But she wants to not mix genders, perhaps, or something like that. Or maybe you're trying to differentiate the students' grades in a very small school, so only the first graders together, only second graders together. So you're trying to keep some kind of a category where they're connected and not separated into different places, like my chocolate and my vanilla. And so she puts them on these rows or in these groups that have to be the same size, so therefore it has to evenly divide the number of people in each of those categories. So I thought that one was a very clever example when I saw that one given. The person doing it was actually putting them in rows by gender on that particular example. What do you think? Okay, let's try some group work. You have 3 group work problems from this section, and this one will be due on Monday.